Hey guys, Mr. Rast here, and I just have a confession to make. I am one of those guys that likes to play chess with old men in the park, although it is difficult to find 32 of them at times. Welcome to lesson 2 of topic 10. We're talking about kinetics, and today we're going to talk about different types of reaction mechanisms. So, before today, we talked about different types of reactions. We talked about exothermic and endothermic reactions. And if you ignore this big hill here, we talked about changes in energy. And if a reactant has more energy than the product, and I didn't have this hill, I just kind of drew two lines before. If the reactants have more energy than the products, that means energy had to leave the system. And if energy left the system and the product has less energy, this is an example of an endothermic reaction. What I have here, this hill kind of helps explain rates of reactions and what's going on here. So we're going to do this reaction, and this is something we did the last lab, or a lab that you have done this year, reacting hydrogen with oxygen. And when we put magnesium and hydrochloric acid. Hopefully you've done this lab. It released hydrogen gas, and in the graduated cylinder it was upside down, and I might have come by with a lighter or something like that and lit it, and that was the hydrogen gas was reacting with oxygen in the room, and if you remember, it turned into water. It made the whole graduated cylinder, it made a bunch of water condensate in there quickly. So anyways, the oxygen and the hydrogen were able to touch each other. If you remember the collision theory from the last lesson, they were able to touch each other in that graduated cylinder, but they weren't reacting. They needed a little kick. I had to put a match to it or a flame or something like that. So what's happening here is when you add energy to it, the hydrogen, remember, the hydrogen is the big ones, or the small ones. Hydrogen is the small ones, and oxygen is the large ones. When I add energy to it, that allows them to collide together with more force. And so we're adding energy and it's pushing them together with more force. And you kind of get to a point where everything's colliding together. And I made the analogy with the collision theory before about cars crashing together. So we have these cars crashing together. Remember the story? So they might crash together, but if they don't have enough force, they bounce off. And at this point here, they're not cars. This is the reactants, two separate cars. At this point here, it's kind of like one big thing. It's not quite the product of the cars crashing together, and it's not separate cars, but it's kind of this one situation. So at the very point up here, it's kind of a combination of everything. It's very short-lived. If I had a high-speed camera and two cars were crashing together, and I could pause it right here, the next frame either crumpling together or bouncing apart would be telling on what's going to happen. So they get to this point here where everything's kind of crushed together, and if there's enough energy, the reaction keeps going, and then it starts breaking apart. And if you take a look here, now the oxygens are not connected and the hydrogens are not connected. The hydrogens are connected to the oxygens, and this is water, H2O, two hydrogens and an oxygen. So if we take a look here, we have the oxygens and hydrogens coming together, colliding together, and then we have a new product being formed. What's important about this is it took energy to make this collision happen. They weren't just at our normal conditions. The hydrogen and oxygen weren't reacting in class, even though they were touching each other. It took some energy to make this happen. The energy needed to make this happen, that's kind of like it's illustrated here in this diagram, but the energy needed to make a reaction happen is called the activation energy. This is the minimum energy to make the reaction happen. So by adding that flame, by adding that match to your hydrogen and oxygen, that's what made the reaction happen. I had to add some energy to it. When this happens and you have that brief moment of everything colliding together, this is called the activated complex or the transition state. This would be, as a molecule, very, very unstable. This is H4O2. It's a very unstable, short-lived molecule. Just like when a car collides, there's a moment where they're just touching, but then it quickly, it's a split second. So this here, it's a fraction of a second that this exists, but that's called the transition state or the activated complex. That's when everything is all together at once. The other thing you need to note about these diagrams is the overall change of the reaction is the difference from the reactant to the product. So it's just from the reactant level to the product level is the overall change of this reaction. Sometimes people get it wrong and they'll say the change of reaction is from all the way at the top, the activated complex, all the way down. But energy is conserved. So that means the energy needed to add to make this was also released. So at this point here, there was no change in energy. So the change in energy is right here. This is an exothermic reaction. We are losing energy. The product has less energy than the product, or the product has less energy than the reactant. Water has less energy in its bonds than hydrogen and oxygen has in its bonds. We could also have endothermic reactions, and what that would look like, I don't have a picture of it, but pay attention here, maybe you could put this in your notes, is if it's endothermic, it would still have an activation energy, which would be this here. But in an endothermic reaction, instead of ending lower, it'll end higher. So you might have an activation energy and then the hill will go down here. And so if the line was right here, instead, if that's where the products was, the products have greater energy than the reactants. So the overall change would be the distance from the reactants up to the products right there. That would be an endothermic reaction. This is an exothermic reaction. Here, just kind of another illustration of this all together is we've got a methyl chloride. We're going to say this little spotted one is chloride, and we're going to say that fluorine ion is going to react with the methyl chloride. And as the fluorine ion collides with the methyl chloride, you'll get to this activated complex where, if you guys recall, carbon has 4 valence electrons, so it likes to make 4 connections. At this point here, it's got 5 connections. There's 10 valence electrons around this carbon. This is a very unstable situation. Carbon, a lot of times at the beginning of the year, kids say like, hey, can this happen? Can this happen? It's like, yeah, they can, but it's very short-lived, it's very unstable, and it'll break apart. So yeah, you can exceed the octet level with carbon, but it's very, very, very brief. And at this point here, we've got a fluorine connected and a chlorine connected. But what's happening is as this fluorine is connecting, it's not really very strongly connected. And what's happening here is the chlorine is starting to break off. So it's kind of a moment where they're kind of, one's adding and one's breaking apart. But it's a very short-lived, unstable arrangement. And it may break apart to reform the reactants, or it may form the product. So check this out. You could add activation energy and it goes up here, but it's not quite enough and it will just go back down. It's almost like rolling a ball up a hill. So you might give it some activation energy and it might not quite go over. And or you give it enough activation energy and it actually makes it over the threshold, over the needed energy that you have, the activation energy, and you'll go all the way over the hill and create your product. So here is a short little demonstration of that.
When a fluoride ion approaches a methyl chloride molecule, a bond begins to form between the fluoride and the carbon. The molecule's carbon-chlorine bond lengthens and becomes weaker. The energy of the system increases. As the carbon-fluoride bond forms and the carbon-chlorine breaks, a configuration of maximum energy is reached, called the transition state. As the reaction proceeds to completion, the energy of the system decreases.
So I really like that video because it shows kind of an illustration of how this is happening, how as the fluorine starts to join, it starts to become, it takes energy for this carbon to now be making these multiple bonds, and then it will start to release energy as the fluorine connects. And in this situation, this is an exothermic reaction because the products have less energy than the reactants. Again, from this point up would be my activation energy. From this point down would be my change in reaction. And the molecule at this peak, right there, hard to match it, right about there, this would be my activated complex. Catalyst! So a catalyst is any substance that speeds up a reaction without being used up. In organic systems, catalysts are enzymes. They're large proteins. And hopefully you've taken biology before you've been in chemistry, so you've heard about what enzymes are. They're a large protein, and they work like a catalyst by this large protein. Now remember, reactants, if you remember the collision theory, they have to touch each other. They have to touch each other with enough strength and in the proper orientation. A catalyst is a substance that makes the reaction go faster without being used up. It speeds up the reaction by giving it a new path. So it's a new way for this to react. The new path has a lower activation energy, and it makes the reaction go faster. So if I think about this protein, I'm just making up something, some enzyme, and I've got my two reactants. They have to react together. Okay, my two reactants have to react together, and I've got this enzyme. The enzyme may attract and bond with one of those reactants, and so it locks into one of those reactants, and then it locks into the other reactant, and the reactants change the tertiary structure of the enzyme. The tertiary structure is the shape of the protein. So it locks in these two reactants, and it changes the shape, and that shape kind of puts them in the right orientation and really just puts them together. And so it grabs one, grabs another, puts them together, and then it releases them, and this product goes. So these two reactants, one goes in, another one goes in, the enzyme puts them together, and then it releases. That's kind of how, a very simplistic explanation of how biological enzymes work. Anything that blocks the enzyme from behaving like, or I shouldn't say just enzyme, but blocks a catalyst is called an inhibitor. So in biological systems, you might take something because, like maybe a painkiller, you don't want this signal to constantly be moving. And so when you have an inhibitor, it will block where maybe one of those reactants would go. And so the enzyme can't now connect together because there's something inhibiting the enzyme from working. So inhibitors block the enzymes, and therefore it doesn't lower the activation energy. So let's watch a video of a demonstration with hydrogen peroxide reacting with a catalyst.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
So this is a really cool video, I think, because it shows what hydrogen peroxide does. Hydrogen peroxide will decompose naturally and produce oxygen and water. And the reason you put hydrogen peroxide on cuts is the dirt and the debris in your cut. You're doing that to clean out your cut. It will react. This is a very concentrated hydrogen peroxide, but it will react with the dirt and the in your cut, and it will start to create oxygen bubbles and water. And those oxygen bubbles will agitate, will kind of pull up that dirt that's stuck in your wound, these bubbles, and it will kind of flush it out a little bit better. It's a better cleaner, and then you wash that hydrogen peroxide out. If you don't have hydrogen peroxide, you use water, but when you have a wound, your nerve endings are exposed, so it hurts. So when you have hydrogen peroxide, I know it doesn't tickle, but it's reacting, and those nerves are exposed, so it kind of hurts. But the alternative would be to kind of like scrub, get that water and really clean it out well, and that hurts actually more. So for what it does, even though it might hurt to put hydrogen peroxide on there, for what it's doing, it's actually a lot less painful than actually trying to like scrub all that dirt out manually. Okay, so what are we talking about here? So if we have a catalyst, what that's doing is it's lowering the activation energy. So the reactants and the products, the change in energy is still the same, but it's lowering the activation energy. So if you see an illustration like this, and it's very common on chemistry tests to see illustrations with the high activation energy and a lower one, and they'll ask like, what is this? What's going on? If you see a picture like this, it's always indicating that there's a presence of a catalyst. So this would be the catalyst with lower activation energy than your original situation. How catalysts work? Well, one catalyst, a great catalyst, is platinum metal. And what platinum will do is when there's a presence of a gas around it, the gas particles will actually attach to the platinum metal. So hydrogen bonds to the surface of the metal, and so that it bonds and then it can also release. It breaks the hydrogen-hydrogen bond. So if you have platinum metal and there's hydrogen around, the hydrogen-hydrogen bond breaks and it can connect to the surface of the metal, but it can also reattach and float off. It's free to come and go. If we have a carbon-carbon bond, a double bonded here, this is called ethene. It's a carbon-carbon double bonded with 4 hydrogens around it. It can do the same thing in the presence of platinum, where it can break that double bond. It breaks the double bond and it can connect to the surface of the platinum. And when it connects to the surface of the platinum, it could then break back off and float away, or as it's on the surface of the platinum, those hydrogens, so the double bond breaks and it bonds to our catalyst. The double bond breaks and it bonds to the catalyst. The hydrogen atoms can move around and associate with the carbon. So the hydrogen atoms can bond with the carbon, and if this happens and it breaks off, now instead of having a double bonded carbon-carbon with 2 hydrogens around it, you've got, 2 on each, so that was 4. Now you've got a carbon-carbon with a single bond, not double bond, it was 6. So you started off with this situation here, a double bonded carbon. It attaches, the hydrogens connect to it, and then it breaks off. And so this offers another pathway, another way for this reaction to occur. And that's what catalysts do. If you notice, the platinum wasn't affected at all in this process. And here I've got a great illustration of this. And in particular, it's a very important reaction we're going to see here because it's what catalytic converters are. They're in your car, and what they do is they prevent smog. And by running your exhaust, which has smog, which is nitrogen monoxide, across these platinum plates, and the platinum can act as a catalyst to reduce the amount of smog that gets released from cars.
In a platinum-based catalytic converter, nitrogen monoxide molecules in the exhaust stick to the surface of the platinum. The molecule decomposes, each atom remaining on the surface. When another NO molecule comes to the area, it also decomposes, and its N atom bonds with the other N atom on the platinum surface. The O atoms also combine. The gaseous nitrogen and oxygen molecules then float away from the surface.
So you should take from this that the platinum's not changing at all. It's just that the presence of it allows the nitrogen to bond with it, nitrogen monoxide, which then breaks apart, and then another nitrogen monoxide comes, breaks apart. The nitrogens and the oxygens can connect to each other on the surface of the platinum, and they float apart. So it makes this reaction, it makes this process a lot easier to occur in the presence of a catalyst. All right, so let's talk about reaction mechanisms. First of all, what we've been dealing with has been elementary reactions. This is a reaction that happens in a single step, where a reaction mechanism is a description of how a reaction really happens. So we normally just kind of think, talk about a single step that something happens, but a reaction mechanism is showing what really happens. It's a little more complex at times than a single step. It's a series of elementary reactions. It's a series of reactions that happen one after another in quick succession, and you most of the time don't even realize that they're occurring. The product of an elementary reaction is an intermediate. So these reactions will happen, they'll produce intermediates, and then the intermediates will react to form something new. The intermediate is a product that immediately gets used in the next reaction. So we talked about reactions before, somewhat of elementary. It's a single step, okay? A reaction mechanism is a reaction that occurs with multiple steps. It's a series of elementary reactions, but the product of every elementary reaction is called an intermediate, which then gets used to follow the next reaction. Let me illustrate this for you here. So in this situation here, we have a reaction mechanism. So before I just had one bump, and then it was the product. Where here you've got multiple steps, and then you've got your product. You should take a look at this and be able to answer, is this an exothermic or endothermic reaction? Hopefully you can see this and see that it's exothermic, because still the reactants have greater energy than the products. The products have less energy. So this is exothermic. It could also be endothermic. It could have been up here. But the important thing is that this reaction occurs in 3 steps. There's going to be a reaction that will, and then another reaction, and then another reaction. The activation energy for the first reaction, the first step, is fast, and that is relative to the other reactions, in particular the second step. So this is the activation energy is fast in this one, and therefore it has low activation energy. It doesn't take as much energy to get over this. And if you think about like rolling a ball over hills, you'll be able to roll it over this hill easier than rolling it over the second hill. The second hill is has higher activation energy. This is a slow step. It's more difficult to get over this one. So this step will slow down the reaction, because not everything will make it all the way over this second step. It's important to note that energy is conserved. So if you have enough energy to get over the first step, you will have enough energy to get at least partially up this next one. But if you don't have enough energy to get over to actually reach the activated complex, then the molecules will go back into the reactants. They will not stay in the middle. They won't. It's not a roller coaster that has friction, where the reactants will actually stop in the middle. So they either won't make it up, or if they make it up, they'll go up here and then come back, but they won't get stuck in these valleys. The third step is also fast, and it has low activation energy. And it would be worth noting here that if you were able to get over this threshold, you would inevitably get over this one, because you will be the energy here will be, you'll get so much energy out of this that it'll easily be enough to kick you back over. And I think about this with like kinetics of a ball rolling. So if I was going down here, I'd easily be able to get over this hill. So what this is saying is that the second step is rate determining. This is the step that determines if this reaction occurs or not. So that is a rate determining step. In this situation, the second one was, but is it possible that the first one was big and then the next two were smaller? Definitely. This illustration, the second step is rate determining. That does not mean that the second step is rate determining for all reaction mechanisms. They're all unique, they're all different. In this example, the second one is the largest one, therefore it determines the rate of the reaction. What gets, like if you just think about in the earlier lesson, earlier in the lesson, if you just were to react here and make a product here, and this was just one elementary reaction, you have this product at this situation. This product gets reacted in the second step, and then it makes a new product, and then it reacts, and then it makes the final product. These products are very short-lived. We call them intermediates. So at this point here, you've got 2 intermediates. So for a 3-step reaction, you're going to have 2 intermediates. In a 3-step reaction, you're going to have 3 activated complexes. There's going to be 3 points where you're going to have a very unstable molecule forming. So there's high energy here in this molecule. It's not a stable molecule, but if you can look here, the second step would be the most unstable molecule formed. This would be a very unstable molecule. It takes a lot of activation energy for it to happen, and then therefore it's going to release a lot of energy when it's allowed to break down. So there's 3 activated complexes. So what we're saying here, with if you think about that last diagram, is there's an activation energy for each elementary step. Each elementary step has a different activation energy. And it's the slowest step, the hardest one to get over, is the rate determining step. This will have the highest activation energy. So the highest activation energy will be the slowest step, the least amount of reactants will make it over this step, and this will determine the rate of the formation of the product, which is the rate of the reaction. So here we've got a reaction of ozone. We have ozone, O3, and it breaks down to make O2. If we balance the equation, which we've done before, we would say that it takes 2 ozones decomposing, and it will produce 3 oxygens, because we just balance O3 and O2. We put a 2 and a 3 here. And this should be familiar with you at this point. But this process is not a single step. We look at these things, and there's more to it behind the scenes, and that's what we're talking about now. This is a multi-stage reaction. So the first thing that happens is ozone, it's a very unstable molecule in itself, can break down to produce oxygen, O2, and a single oxygen atom. Now, oxygen is diatomic. It doesn't exist as a single atom, does it? It only has 6 valence electrons. This is a very unstable situation. And so when this ozone breaks apart, this unstable oxygen will clash quickly into another ozone, and that will make 2, it breaks off one of the oxygens from the ozone because ozone's already stable, to make 2 oxygens. So as a net result, if we look at this as a basic arithmetic problem, we can say on the reactant side, I've got 2 ozones and a single oxygen, and then I've got 2 oxygens and a single, 3 oxygens, there's 1 here and 2 here, and a single oxygen. What we add up these 2 ozones and we put a 2 here. And see, there's an oxygen on both sides, so these guys cancel each other out, and then we've got 3 oxygens here. So the net is what we see down here. So let's watch this illustrated.
Gaseous ozone decomposes in 2 steps. First, 1 oxygen atom splits off. Next, the single oxygen atom reacts with a second ozone molecule to produce 2 molecules of O2. The product of the overall reaction is 3 O2 molecules.
So again, it's just worth noting that it's not 2 ozones just break apart to make 3 oxygens. There's steps involved, and each of these steps have different activation energies. And I would guess that this first one would be the rate determining step, because producing just a single oxygen, this is very unstable right here, just a single oxygen, and that single oxygen will rapidly react with another ozone to make this O2. So I would probably say step 1 is your rate determining step, because this is a more unstable situation. I'm just guessing, I don't know. Let's take a look at a 3-step example, and you'll see that it gets considerably more challenging as we add more steps.
Hydrazine is formed in aqueous solution in a 3-step process, each step being bimolecular. First, a molecule of ammonia reacts with a hypochlorite ion to form chloramine and a hydroxide ion. Next, the chloramine reacts with a second molecule of ammonia to form a charged species with a nitrogen-nitrogen bond. Finally, the charged species reacts with a hydroxide ion to form hydrazine and water.
Okay, very good. So you can see here that it's making, there's a lot of steps in here, but the same is going to be true of what our last one was, that we have an ammonia and another ammonia. That's why there's 2. We have a hypochlorate. But if you notice here, this hydroxide cancels out here. These 2 guys cancel out. We have these guys canceling out. We've got these guys canceling out. So things that appear both as a product and a reactant cancel each other out in the net overall reaction. It's also worth noting what's special about this one is this final product isn't just everything from the 3rd step. We have 2 things from the 3rd step, but this chloride ion was produced from the 2nd step. So it's not that at the 3rd step everything forms. You might get some things forming in earlier steps that aren't used up in other steps. So that's why this chloride is here. It actually gets produced in the 2nd step, and it's not anything to do with the 3rd step. So I'm not going to ask you to predict or make these steps, but I just want you to appreciate that when we see a reaction mechanism, that's what those humps mean. It means that there's multiple steps. So I want you to understand the concept of it. And so that's all for reaction mechanisms. I hope it's a little more understandable to you right now. If you have any questions, let me know. I'd be happy to help you, and I'll talk to you soon.